Recall, a sequence is a list, and a series is a sum. A geometric series, then, is a sum of terms in a geometric sequence. So we did sums with arithmetic. Now we're going to do sums with geometric, and we've got a new formula. The sum of n terms in a geometric sequence is a1 times the quantity 1 minus r to the n divided by the quantity 1 minus r. All right? So, number 5 says you received a gift. We're back to this again. You received a gift on the first day of each month for a year, starting with $50 on January 1st. With the amount doubling each month, what is the total amount of gifts received? So last time we saw this question, it was just what did we get December 1st? Now it's what did we get January plus February plus March plus what's the total of all of that? So what's the sum? You still need the same pieces of information. You need A1, that's 50. And you need R, in this case that's 2. We're trying to find the sum of the first 12 amounts. So according to that formula, A1 is 50 times 1 minus 2 to the n. Notice it's not n minus 1 this time, it's n, so that's 12 over 1 minus 2. That's the formula. So when you type this in, you have to be careful with your calculator and make sure you use parentheses appropriately. 50 times 1 minus 2 to the 12th. Close it. And if you're going to type in the whole denominator, 1 minus 2, you got to have parentheses. Otherwise, I think it's probably wise to just do that bottom in your head. 1 minus 2 is negative 1, so you could just divide by negative 1. But either way, practice on your calculators. Make sure you get this, 204,750. $204,750. So that's a nice little chunk. Number 6, find the sum. And so you see that sigma symbol, but it's the same thing, okay? We're doing the same thing. N is 8, so we're finding the sum of the first 8 terms. And it's not necessarily just because this is an 8. It's because if you look at both of these numbers, if you plug in 1, 2, 3, 4, 5, 6, 7, 8, you're going to end up adding up 8 things. So that formula would take the first term times 1 minus r to the 8th over 1 minus r. So we're still going to need the first term and r. You can tell r because r is just going to be the base on the power. So look for the exponential part of this and the base 5 here. That's the r value. The first term is found by plugging in that first number right there. So plug in a 1. 4 times 5 to the first. 4 times 5, that's 20. So A1 equals 20. And so we can see what needs to get plugged in to our formula. A1 is 20 times 1 minus R was 5 to the 8th power over 1 minus 5. So again, be careful on your calculators when you plug that in. 20 times 1 minus 5 to the 8th divided by, I'm just going to do the bottom in my head. 1 minus 5 is negative 4. I think that'll be easier to avoid mistakes. Basically 1.9 million. 1,953,120. Now, number 7 is a little bit different because it goes dot, dot, dot at the end, okay? And what this is an infinite sum. And so it's a little bit hard to imagine at first. We're adding up an infinite number of numbers, and it's going to add up to something. So that seems kind of strange. We still only have one formula at this point, though, for a sum. The infinite sum, or the sum of the first infinity terms, is still going to be A1 times 1 minus R to the infinity over 1 minus r. So that's kind of weird. We can't really plug in infinity. But I can see a1 is 4 really quickly. And then think about how you're getting from term to term. It looks like we're dividing by 5. You can't really say divide by 5. We got to think about this as multiplication though. So we're going to call that 1/5. R equals 1/5. So as I plug this in, a1 is 4 times the quantity 1 minus 1/5 to the infinity over 1 minus 1/5. Okay. Now we gotta take a sidebar here because 1/5 to the infinity is something that maybe we've never dealt with before. So think about 1/5 to the infinity. This is a calculus concept of a limit. If I had the limit as n approaches infinity of 1/5 to the n. Okay, that looks like a calculus problem to me. Basically, imagine plugging in a really, really, really large number. So if I did 1/5 to the 5th power, all right, 0.0032. If I did 1/5 to the 8th power, okay, it's really small. It's getting smaller. 1/5 to the 10th power. Okay, there's that e again, right? It's a really, really, really small number. You move that decimal over 7 places, you're going to have 6 zeros in front of the 1. If I do 1/5 to the 15th power, it's even smaller. To the -11th, you're moving that decimal over. It's getting really, really, really small, or if you think about it, it's getting really, really close to 0. Okay? It doesn't actually equal 0 like my calculator says, but it's getting really, 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 really small. So small, in fact, that we can kind of say this is approaching 0. And so we can treat it like 0. And if you do that, you'd have 4 times 1 minus 0 over 1 minus 1/5 is 4/5. Well, of course, 1 minus 0 is just 1. And so 4 times 1 is 4. We have 4 over 4/5. If you're going to divide fractions, you can multiply by the reciprocal. 4 times 5/4. 4's cancel. You're left with just 5. So I think it's kind of interesting that we are adding up an infinite number of numbers, and we end up, those things add up to 5. And I guess it makes sense if you think about this number. You keep dividing by 5, divide by 5, divide by 5. You end up at some point adding on something that's pretty much 0. So after a while, you're not really changing the value at all. That answer is 5.